This is Physics 2212, Lab 3. Introduction. The purpose of this lab is to predict circuits behavior computationally containing series and parallel resistors in a circuit. So we're going to say that the system is the circuit and the surroundings are everything else. Let's talk about our principles. First of all, the node rule, which states that current flowing into a node is equal to current flowing out of a node, essentially a conservation of current, and the loop rule, which is that the sum of all electric potential differences, also known as the voltage, around a loop is equal to zero. Thirdly, we're going to use Ohm's law, which is that a current through a conductor between 2 points is directly proportional to the voltage across the points, or the electric potential difference. So the charge conservation of energy in circuit. So here we have this circuit. We have two batteries, each of 1.5 voltage, meaning we have 3 volts total. And then we're going to add up the resistance because they're going to be in series. And the current in I1 and I2 are going to be the same because it's all in series. And then we use V equals IR, and we get 441 amps. So what happens when we reverse the connection of one of the ammeters? Essentially, nothing happens. It's going to be 0.02 and 0.02 here. So what if we replace one of the ammeters with a voltmeter? What happens? Well, essentially, the ammeter is going to read 0 volts or almost 0 volts because the voltmeter has a very high resistance. So very little current is actually going to get past the voltmeter and into this area. But the voltmeter is going to continue to read minus 3 volts because there's no drop in voltage. So for this, we can use the loop rule, which states that VB minus the current at the R47 resistor minus the current at the 100 ohm resistor is going to be 0. And then we can work out the voltage from each one. And if you add all of these up, well, it's 0.02, but that's a rounding error. It should most likely be 0 due to the loop rule. And then if you look here, what happens when you attach a voltmeter? The circuit changes. Why doesn't the ammeter reading change? Well, that's because the voltmeter is extremely high resistance, so very little charge actually flows through it. So you're going to see this basically drop, and then drop even further. As we get to the ammeter, it will be almost 0. So what happens if we now replace the voltmeter with an ammeter in parallel with the 100 ohm resistor? Well, first of all, the ammeter has very low resistance, so electrons will flow through it instead, and therefore the overall resistance of the circuit will decrease. And the total resistance is now only going to be 47 ohms instead of 147 ohms. Alright, so now we can work out the total resistance of each circuit element. Essentially, we find out the resistance, we go R47, 48, R100, 102, 0, 0. And as you can see, these numbers are different by very small amounts. That's most likely a rounding error. If we use more precise results and more precise rounding, we would have a much better output in our calculation. All right, so now let's talk about RC circuits. So here we have charging and discharging. And if we have 20 ohms, it's going to be 20 seconds. If we have 30 ohms, 30 seconds. And if we have 10 ohms, which I forgot to write up here, it's going to be 10 seconds. So here we can see a graph of if a 9-volt battery, a 200 capacitor, and a 30 ohm light bulb are connected in series, what is the RC value? Well, the predicted RC value is going to be 30 times 0.2, which is 6 seconds. However, if we do -1 over the slope of this graph, which is minus 0.1667, we're getting a 6.01 seconds, which is pretty close to this amount. Let's talk about potential sources of error. So first of all, we're working with a computer simulation, not in real life experiment. So there really should be no error. Therefore, any errors or discrepancies are from human error, such as, calculations, rounding error. So what if you were doing this experiment in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter and how would it affect the circuits you hooked it up to? Well, first of all, an ideal ammeter has no resistance, which is the ammeter that's used in our model. But an actual ammeter has very little resistance anyway. It would have some, but very little, so the readings would only be slightly different. And then what if you were doing the experiment in real life and used a real battery to charge a real capacitor with no resistance in the circuit? How quickly would our ideal model predict the capacitor to reach full charge. Would this prediction happen in real life? Explain. Well, if there was no resistors, the capacitor would charge up immediately as there was no resistance. However, the wire has resistance and therefore that would not charge immediately and therefore the whole thing would take some time.